All right, week 114 of building my own operating system. What's up, everyone? What is up? Yeah, back at it. Today we'll do a bit more scheduling stuff, I think. This is a pretty deep topic, and so we're spending quite a bit of time on it. But yo, people in the chat. What's up, Lizard? Nice to see you. VA80, Bikram, what is up? Nice to see everyone. So I got a bit of a special announcement today. Today's stream is sponsored. And so before I get into the stream, I want to give a shout out to my sponsor. Yeah, thank you to Let's Get Rusty for sponsoring today's stream. If you're watching this, you've probably heard of Rust. Rust is a systems language with modern tooling and safety guarantees and is actively used by companies like Amazon, Microsoft, and Google. If you've been thinking about learning Rust, Let's Get Rusty is the go-to place for both personal and corporate Rust training, and they've helped thousands of developers learn Rust and also assist with job placement. They're running a new cohort next month. Spots are limited, so now's a great time to check it out. Visit letsgetrusty.com/startwithmark to find out more. You can find a link below. And a big thanks to Let's Get Rusty for supporting the channel. So with that said, let's get into today's stream. We got some excitement in the chat. Is the chat widget working today? I feel like I'm seeing a bit of an absence in the chat widget, so let me double check on that. I feel like I'm not seeing some messages, so I think I need to give my test 0, test 1. Okay. When I do the test 0, it starts popping up. Okay. It knows when it's coming from me, apparently. So yeah. What's up, everyone? I hope everyone's doing well. Feel free to give a bit of a check-in on how you're doing today. I'm doing all right. I'm feeling a little bit low energy today. So just putting that out there, but yeah, we're still gonna have a nice stream. Test N2, VA is doing great. What's up? What's up, Bet Kitty? Anything else to? Working on a Zephyr I2C driver. Happy Easter for all who celebrate. 113 weeks of backlog to cover. If you choose to take on that adventure, it's there for you. Let's also get the break timer running. Okay. Anything else before we get started? Yeah. So sign up already for the Rust thing, even though I already know Rust. All right. I don't know Rust, but I want to learn it at some point. So definitely seems interesting to me. Let me see. So I've got a few ideas about how to proceed today. Over the last couple weeks, we've been working on all the threading and kernel threads and that kind of stuff. There's a lot more work to do. I'm just gonna jot down a couple notes. So I think one thing I was seeing is a weird crash with tasks with the task landing pad. I think I noticed that at the end of last stream. So that's one thing. Then another thing is like this, I want to refactor the scheduling policies. they shouldn't need to be aware of the idle task. I think the way I did the idle task handling last time wasn't the best. Let me visualize. So what I did last time, okay, so basically I introduced the concept of an idle task last time. And it's just this task that always gets inserted into the start. What's up, hello code? What's up, Phasons? And if there's nothing else to run, the idle task is always a runnable task. And it's just, there were actually a lot of problems with my idle task. It looks like this. I mean, one problem that I realized is that the idle task is really only meaningful if we have preemptive multitasking. Because currently we don't have preemptive multitasking. It's all cooperative for the moment. And that means if the idle task is running, then none of the other tasks were runnable. And so maybe the idle task gets CPU time, but that doesn't fix the fact that the system is just like globally like deadlocked basically, because none of the other tasks are runnable and nothing is going to make them runnable without some kind of preemption. Because the idle task is just going to be there and technically it's going to run and be doing yields, but it's not like any of the other tasks are doing anything that are making progress. And so that's kind of an issue. So I'm going to kind of write down some problems with the idle task problems. It's actually useless without preemptive multitasking. That doesn't mean it's useless to try it and like kind of get the basic idea of it working in the scheduler, but we shouldn't expect it to really be useful until we have preemptive multitasking. So that's one thing I noticed. But anyway, but ignoring that for the moment, I think it's still a reasonable idea. And the way I did it was kind of bad though. So the round robin policy used to be a lot simpler, but I added some logic to make it aware of the idle task. And so now as it goes and searches through the tasks, it's explicitly not going to select the idle task in its search, because we only want to run the idle task if nothing else was runnable. And so last week we were seeing that it was actually selecting the idle task even though other things are runnable, which is not what it should do. And so what I've done, so now I basically just, here's where it returns the idle task. It's just the first task. But even the fact that the policy is aware of the idle task is not really good. I think the policy should just be handed a bunch of tasks. It should just look through them and it should return like a null pointer or some kind of null in case it couldn't find anything. And then the base scheduler should take care of selecting the idle task. So that is going to mean some changes, and I'm still figuring out the exact order I want to do things, but that's one idea, and that's described by this set of stickies. Then some more ideas with this whole stack stuff we were doing last time. We were like mapping stacks in kind of interesting ways. And I have some ideas about that. As a refresher, the problem was that in my prototype, I was pointing the stack. I was using the fizz map for the stacks, which is kind of dangerous. It's not something you really want to be doing. You really want to be mapping stacks explicitly somewhere else in the address space. But to do that, I feel like it requires a memory allocator or something, some kind of memory allocator to get pages from the virtual address space. I don't have that yet. So my idea was to do things with static allocation. I put the stack directly in to the task struct, which is kind of a bad idea, but it allowed us to experiment a little bit with doing this. That's a general area we could proceed into. So mapping stacks. Continue with the static allocation approach, but don't map them directly in the task struct. These are some options. So let's just get started with this weird crash. I feel like I was seeing a weird crash last time, and I want to understand it better. Let me see. I wasn't. So currently the kernel is configured to do our set of tests. It's running these tasks that say hello, do some counting, do some yielding, then exit. Okay, crashes without the exit. Here we go. So let's just run the kernel. So here's what we were seeing last time. And that's working. But there was this problem where if I didn't do the explicit task exit, I think it crashed. Oh. Okay, never mind. Interesting. It is working. So okay, I'm not sure why I had that comment. I thought I saw some crash, but it does seem to be working. Just to be sure, I'm gonna, yeah. I'm just gonna, is it really working? Okay, yes, Penguin 2. Okay, so that is weird. Okay, cool. That's good news then. So that was a phantom ghost bug. Let me see. So there's a number of ways we could proceed here. There's a bet kitty working on my own X unit test style framework in C++. Oh, cool. What's up, AB Ryan? What's going on? Working on an OS. That's what's going on. Okay. So I'm accumulating my library of whip commits. Let's think. Okay, so that was whatever. That wasn't real. Okay. Refactor. Let's talk about this. And also another thing I want to kind of get into is how to do integration tests. There's a lot of things we've been coding in the last couple streams that would be interesting to think about testing for. For example, the task landing pad. Yeah, stuff like that. So that's another something we could try. Okay. Let's talk about the scheduling policies. So I was telling you about how I don't really like how it's done currently. let me see if I can find. Here's the commit that introduced the change to add idle task awareness. And so we're doing, instead of returning null pointer, we always just return the first task, which is assumed to be the idle task, which is, first of all, that's an assumption that this thing needs to make. We're also adding this code that explicitly skips the idle task. And yeah, in general, it sort of bakes in this knowledge about the idle task into the policies, which I don't really love. And so let me think about a different way to do this. But first of all, I guess, what is a test setup for this? So the idea with testing around the idle task is that we just don't or maybe we can have one task that just exits. And so this should trigger the idle task. So we're going to run this first, and then we're going to hit the idle task. And one other issue I think was I was in my implementation, I made it a static, I made it a static member, and that was a way to work around some of this template stuff, but then I realized I think another solution would be to do an explicit instantiation of this. I just don't love kind of bloating the class with stuff if I can avoid it, so that's another tiny to do. What I'm just going to do is I'm just going to say, I'm just going to log idle task running. So now we're just going to see that a lot of times. We can even just have a counter. So now, yeah, cool. That's what we expect to see idle task running. So that's a bit of a basic. And so let's think about this a little bit. So here's how I did it. I was just automatically adding one task always to the list of tasks. And that is the task list that gets passed to the scheduling policy. And so that causes a bunch of problems because now the policy needs to be kind of aware that one of the tasks inside this task list is going to be the idle task. So that's and the idea is to not, the policy shouldn't need to be aware of that kind of thing. So I want to experiment with a design where the idle task lives externally to this task list, and I need to think about that. So just to sketch it out, something, I don't really task idle task. I keep misspelling this, but something along the lines of this, where we just really have this thing that's just the idle task. And the problem is that it does need to get constructed, and so a lot of this code is sort of relevant. The code, yeah. On this land, like all this stuff is technically kind of shared, so I'm wondering how we can do that. So there's a few options. We could kind of separate things. We could make, like right now, it's a method that constructs a task and adds it to the list explicitly. It also doesn't really help that our stack handling is sort of messy right now. Okay, maybe just for prototyping we can just do it a little bit messily and then clean it up later, and we can just kind of duplicate some of this code. So let me just think. The task, as a reminder, the task looks like this. I'm also looking at our awful idea. But task is mostly just a bunch of data. So it's and it can be, yeah, and it can get default constructed, I think. I'm just looking at this awful idea for the stack, and that's sort of obnoxious. But it's time for the first break, so feel free to join me for a 20-second stand up. All right. I'm just trying to think about how to proceed with the stack thing. So either, like it's like, this was all a bit of a messy prototype we did last time, and it is kind of getting in the way of what I want to do now. So I'm just wondering, maybe I can what happens. So basically, idle task, let's map the stack. Then Yeah, my hygiene hasn't been super good. And what's this? Bit of random stuff. Ooh, yo, what's up, Digitalized? Nice to see you. Oh, I'm a little bit slow today. I'm also having a hard time figuring out how to proceed. But I'm just going to... Let me clean a bit of this up. Okay, there is like a bunch of garbage that is making it hard to move forward. Let's just understand what I did with that whole stack stuff, because I kind of made a huge mess. Okay, first off, there's a bunch of random comments that are just like distracting. Is this whole thing? So we don't need to. So with the new change of having like the statically allocated stacks, we don't need to allocate physical memory for the stack anymore. That sort of already exists. This comment is obsolete. And here's the idea. So we get the stack, and then so we sort of insert something into the list, and we get a reference to the task back that was put into the list, and then now I can actually figure out where the stack is because it's embedded into the task, which is to be clear kind of a really bad idea. It was mostly just for prototyping. I think in the future, either we will really start allocating stacks properly into the address space, or like instead of putting it into the task struct, we'll have like a parallel array of task stacks that the task can use, something like that. There are some implications of that, but basically, so we insert the task into the linked list. We get a reference to it back of what was added. From there, we can locate the stack memory. We compute the top of the stack by adding the page size. Then we compute the stack pointer on task entry, which is p task top minus the size of a pointer for our landing pad. We write into the landing pad, and then we set the RSP to point here. So that is good. And so this was all kind of old code. And then the other consequence was that we don't need to call free anymore, because that's a lot of reinterpret cast. Yes, how many? We got 4 reinterpret casts. That's a good call. Unfortunately, I think they're all necessary. The task register state stores uint64t's, and we're taking pointers and converting them to be stored in the task register state, and you need to reinterpret cast. I don't think you can static cast that. And then likewise, I guess I don't know. Yeah. Yeah, I think they're necessary. It's possible or not. Let's just ask the AI real quick. Are all these reinterpret casts necessary? Going back to the okay, it's doing some reading of the different types and stuff. All four are necessary given the current types. Yeah, so when you're casting from a pointer to a UN64, you can't implicit convert or static cast. So here I'm casting from, it's just it's a function pointer to a void star. Yeah. So Lieben, I'll direct you to the resources page. Okay. Let me I'm just gonna keep it moving a little bit. So the idea is to separately, like, we're no longer going to be like sort of implicitly adding this like one idle task. We're just going to be constructing the idle task that's a part of the scheduler. And I'm just going to make a new function. Did I mess up? Oops. Okay. I'm going to call this so I just want to initialize the task, init task, and it's basically the same. I'm just trying to think if it should return a task by. I'm just gonna go with this for now. It's just going to initialize a task via mutable reference. So we don't have any of this stuff now. We're no longer emplacing into anything. We have the task, and this is like a little bit messy, but yeah, we're just going to task ID, set some fields. Get state, runnable, dot register state. Okay. And what was the 0? This. So this is a little bit, do we still need this? Okay, then this stuff is mostly the same. And I think that's kind of it. So the definition, private. And now that's going to, yeah, this is like kind of bad because it's duplicated code, but it's just going to allow me to call init task. And it'll be kind of similar, actually, init task. I need to pass the midle task over here. Bunch of chat going on. Yeah, I'm just going to focus on coding. So now we're no longer initializing this thing. We are separately constructing the idle task. Just making sure we did that right. And then the next change is going to be to probably yield impl. So now here's now where we change, where so now the policy is no longer responsible for selecting the idle task. So a couple things get reverted here. Let me see if I can do this in lazy git. So when here were the changes, I'm going to apply patch in reverse. Yeah, that looks good. So I've reverted the change. So now the policy, it's possible to have an empty task list, and it simply iterates over everything in this list and selects anything that's runnable. The idle task lives completely separately. It doesn't know anything about an idle task, and it's allowed to return null pointer in case it could not find anything runnable in its set of tasks. And then here's where we handle it. So now it's like if, and the AI sort of knows already what to do. If we did not find a next task in the policy, we use the idle task. Whoa, is the RR scheduler already done? Kind of. It's not really that hard to do the RR scheduler, so it's not like a lot of code. So So yes, the RR scheduler exists in a very basic form. In probably the most basic form possible. Nothing fancy here. No run lists really. The list it receives a linked list of just all of the tasks on the system, no matter what state they're in, and it just searches through the list to look for a runnable one. It's pretty much the exact same thing that JOS did when I was working on JOS. So I'm just sort of taking that influence for a first step. Right. So yeah, that's what that looks like. So now, yeah, so now when the policy doesn't find anything, it selects the idle task and switches into it instead. And if I did this correctly, let's just try it. The kernel should do the same thing we were seeing last. Okay. So that's bad. K-main started. Whoa. That... What? Wow, that is unexpected. You just quickly revert this. Oops. Just quickly bring some of this back. Okay. Okay, so something was up there. And I think we can debug that. For a task, is there a specific reason for using raw pointers over smart pointers, or to use with JOS still? Yes, raw pointers. So we see a couple raw pointers. There's a raw pointer here, a raw pointer here. And the reason it's not a smart pointer is because there's no ownership of the task. The ownership is in the linked list. And so in C++, even with modern C++, if you want to have a pointer or like reference semantics to an object where it's like you're storing a pointer, but it's also possible, like you also want like nullability. Like I do want it to be possible to pass a null pointer and have the thing handle that. A raw pointer is still the idiomatic type to use there. So I don't want this argument to take ownership of the task. It's just basically a non-owning pointer. So yeah, subcorp mods. Why did you choose to create a new S? Yeah, it was just something I always wanted to do. That's pretty much it. So what did I do? Why? That was such a strange error. Condition. And okay, what first of all, what compiler? Okay, how about okay, It'd be cool if I could jump to that. Scheduler.hpp. So, okay, yeah, so this thing is not bool, it's void. What? What? Why did that work? What? All right. Be back in 20. What? What? Dude, sometimes I just don't know what's going on with my computer. Why? Wait. Why was that? Holy changing this from bool to void fixes things? Yeah, it does. All right, tell me how that makes any sense. What? It's just a method that I am calling. Oh, okay. Yo, what's up, NSG? Nice to see you. I'm doing a little bit of refactoring on the scheduler again. And mostly kind of working on this idle task thing. Rax is somehow 0 to something or not, should that matter? Guess I'm not checking the return value. Wow, I mean, it's just so bizarre on so many levels. I mean, I don't really think it should matter. So yeah, Rax is going to get some garbage value because I'm not setting it, but who's going to be reading Rax? Or maybe maybe the client that's calling the constructor will get a corrupted Rax. That's crazy, because whoa, that's actually wild. I think actually, yeah. There's gonna be a very, very weird Rax, because it's like an uninitialized Rax, which, like, I think the caller of the scheduler CTOR, okay, I don't know. This is like not this is not interesting enough to like spend like an insane amount of time on, but it's interesting enough to spend a little bit of time on, just because it's so bizarre. And so so we got init task, and okay, so init task, and Rax is going to get set to like some like very random thing. It's going to be set to like some thing that's on the stack. Which is RSI, RDI, which is the pointer to the task func. And so we're gonna like accidentally set racks, and then the real racks is the return value register. I mean, it's a lot of different registers, but it's like the return value register, notably. And then but then the real question is, who's the caller of the scheduler CTOR? And it's the kernel. It's the kernel right here. So the kernel is calling the scheduler CTOR, but the thing is, like, is it really going to be respecting a return value? Kernel. So we can see the kernel calls the scheduler CTOR here, but racks is not used. It's not using the return value because it's all it does is it passes a pointer to some memory. So we're passing like 4 arguments. But the RDI is right here, and so it's passing a pointer to the memory for the scheduler as the this argument. But racks is actually never used. Racks is just like overwritten. So I'm going to stop the investigation here. That's like freaking weird. What was going on there? But yeah, let's get this back to void. Okay, so just to like focus a little bit, what I was just trying to do, a refactor of the scheduler that allows the policy to kind of get decoupled from the notion of the idle task. So now the policies don't need to have like all these special edge cases to like select the idle task appropriately. All they do is they just get a container of like possibly runnable tasks. They just do their best to find anything that's runnable and do their thing. If they just can't do that, they don't need to worry about like weird idle task stuff. Like they don't need to assume that the idle task is always the first task in this list. They just return null pointer, and then the core scheduler infrastructure is going to observe that, okay, the policy was not able to find something, time to select our hard-coded idle task. So yeah. So that's just a little bit of a cleanup. Yeah, then sort of the question is how to, like, technically we need this, and we need this, and we need this. These are all sort of like some cleanups. Yeah. Decouple idle task from policy. So now it's a bit more into like software engineering world, but like then the question's like, okay, it's really ugly to have this like init task thing that is basically copy pasted code from create task. So the question is, what could we do about that? So a couple options. We could have a function that just returns a task by value. And then over here, we add it to the list, and then above, we just assign it into the idle task. or we use a constructor, maybe. I was trying to avoid making the task like a super C++-y thing, but it's possible. Okay, let me just zoom out a little bit. That was like super deep. What have we done so far? Super small star. Okay, we did a bit of this. Okay, this could also be possible. A nice little simple thing. So last time I was working on my idle task, and I made it a private static method, which I didn't really love. And I was sort of having this idea of whether I could make it a freestanding function. Oh my gosh, how do I get the AI to help me? Okay. Okay, right. Then there was the problem of this. Maybe that's okay if it comes after. It comes at the end here. Okay, but then it's kind of problematic because then in order to use this right here, we need to have a forward declaration. Okay. It's actually, okay. So that's actually hard. To know the scheduler, so it needs to come after, but then the scheduler needs it, so there needs to be a forward decl. The static private member is the easiest. Okay, I'm just gonna leave it at that. Okay. Let's talk stacks. I think that's another thing that's kind of bugging me. So again, my strange idea that I'm still trying to stick with is doing a lot of static memory allocation, and not having a dynamic memory allocator. Let me think. Yeah. So the idea is we want to have stacks for each task. We want to have them not live in the physmap. We want to have them live in the virtual memory area. And doing so seems like it would require a virtual memory allocator of some kind. Where VM allocator basically we want to be able to, let's just imagine like the allocator is like just given like a big chunk of memory, which it owns. And then you can say things like, for our case, you know, alloc 4K and free, you know, basic operations you might do. And in this case, we're like dynamically allocating stacks based off of when tasks are created and stuff. And so simple things like a bump allocator are not really sufficient because we need to have a working free. So I'm thinking that it's not super trivial to like implement this allocator. Let me just check in NSG has some thoughts. You could allocate physical pages mapped in the higher half as well. In fact, it's better since it's page aligned. You could allocate physical pages mapped in the higher half as well. Yeah, so I guess that's the idea. Is like, well, any kind of page would need to be mapped. Because the kernel heap would be good. Yeah, I'm sort of. That's basically what the idea is, like a kernel heap. I think, to be honest, I find that a little bit intimidating to implement a kernel heap. So I've been trying to not do that, unless it's really necessary. So, and that's why I did this, like, this idea. I want to keep doing this just because I think it's a kind of an unconventional strategy, and I'm just curious to take it more to the end. I feel like the kernel heap is sort of like a cop-out in a certain way. It's just like, it's a very standard solution, but I'm just kind of interested what it will look like. So let's think more about this task. So the stack is currently embedded in the task. Like that's pretty clearly an awful idea. It makes this struct super big. It adds like thousands of bytes of padding in between these things and this thing. So that's pretty clearly a bad idea. Let's think about an alternative way that's maybe a little bit better. And so, okay, let's keep that around, but char k page size. There we go. So what if we make a separate struct and then we have a guard page, which is a new development, but that's actually kind of interesting because in order to really do the guard page, we would need to unmap it from memory. And actually currently my virtual address space code doesn't really do unmapping. So I don't know. That's something. So maybe that's not an idea for now, but as just another idea, we could yeah, instead of storing the stack directly in the task struct, that's kind of a stupid idea. Okay, how do I? Let's come down here. So we're gonna store them in a separate like array. So we have the task list, which is everything is fixed size here, right? So we have these compile time constants of the maximum number of tasks, which is already a bit strange, but we can use that. Here, so array task stack. So we have our parallel array of stacks, and then for the idle task, it's just going to get its own task stack. So let me think. In terms of memory allocation, it's probably best to put these huge things at the end. There we go. Right. These are large. So now we've at least solved a bit of the issue of like having 3K of padding. And we've introduced these large stack buffers. And now we can try to use them. And so let's think about create task. So now instead of getting task.stack, we need to go from the current task to its stack. All right, be right back. I need to draw this out. So let's say we have some tasks. And let's say we have some stacks. But this is our sort of like, okay, we have capacity for four tasks, capacity for 4 stacks. Let's say we have one actual active task. And so it's going to need a stack. So what I was sort of thinking is that there could just be like a one-to-one mapping somehow, where wherever a task kind of ends up in, it can just use the corresponding stack. And I don't know if that's actually really easy to do, because the linked list can look like this, where it's like, you know, the linked list can be sort of fragmented in a weird way, where it's like, let's say first we have this one task, we have another task, and so the linked list looks like this. And so it's 0, 1, 2. But then this task can die, and this thing just went from 2 to index 1. but it's pointed here. So I guess the idea is just, if there were a way just to figure out the index in this underlying array, that could be what we need. I just don't actually know if that's possible to do easily. What's up, Ismail? Nice to see you. So I think I need to, a simpler strategy is to and it's not that different. It's to use some kind of pool of stacks, maybe. So when, let me see. So let's pretend it's like this. And let's say we're out, and so okay, let's say we're doing our first task. Time to create our first task, and we need to get a stack, and so we just allocate one from the pool. And we just need to remember to free this later. So I think, yeah, maybe the pool is a better approach. Let's just imagine a scenario. So in the default scenario, these things just come along and get their stacks from the pool. The 3. And then let's say this one exits. And the next one comes along and just gets another one from the pool. And so yeah, maybe that's just the simplest way to do it. So what's up, Mathru? How are you doing? I am confused. But I'm trying to fix that. So let me try to illustrate that. Okay, what I want to do is, instead of this array, I'm going to make a pool, this ETL pool kind of thing. And maybe I'll pull up the docs. So pool type name team. So let's all learn how to use an ETL pool together. Stack pool. And it's a task stack and k num task. Okay, maybe I don't need this thing. So we get this pool. And then the idea is like, let's focus on this example, create task. Yeah, so now we need to get something from the pool. How do we get something from the pool? Create. Is that how this works? Okay. Okay. So okay. And then now the idea is instead of task.stack, it's p-task stack. I forget this. I'm just going to double check with the AI. Create on an ETL pool, return a pointer to the newly allocated object. It's reading the pool file. Yes. Returns a T to the newly constructed object. Yep, okay. Good call. Good call. Yep, so this is not right. It's point arithmetic on this thing. I need to be doing data.data. So let's rename this to stack, right? There we go. So stack is this std array that's page size like, and then the .data returns the pointer really to the data. Right, then here's the part where we need to remember the stack so we can free it later, right? What I want to ask it is, in the documentation, it also uses this pattern. Where you call allocate and then use the placement new. Docs mention the below strategy of using placement new instead oh, instead of create. I just think, when would you do that? Because that's pretty similar, isn't that pretty similar to calling create? This returns a raw pointer to the memory that hasn't had the object constructed in it. Yeah. They're equivalent. Create is literally just calling allocate plus placement new internally. Oh. Where you need to call a specific non-default constructor. Create is clean. Oh, interesting. Okay. What's your opinion about the current and future job market in tech? Man, that's a deep question. Job market sucked before. It was only good for a very small percent of people moving to code. Nothing could be bad as DEI for us older white males. Yeah. I don't know. What's my thoughts on that? Yeah, it's clearly going to change a lot. I do think computers will continue to be a part of our lives, and so people that understand computers will be able to provide value. But yeah, there's going to be a lot of changes. It's pretty much impossible to say. Okay. Cool. So pretty much that's that. And now we need to remember this thing. So we got this thing. This needs to be freed later. I will also just ask about this. It's saying you need to manually call the docs. Also say you must say to manually call the detour and then call release. Is this really necessary? Or is there an API that does it all? Okay. If I just learned to read, I could just see that it answered all my questions. Calling destroy. Okay. Cool. So let's recreate a little bit of this above in the right? Good. And then lastly, thinking about freeing of things. And so we need to, let's look at the destroy. But iPool, is that different? It's a little bit confusing. Base T is the generic pool, which in itself inherits from iPool. This is a little bit confusing, but I'm just going to go ahead and call destroy. So we need to adjust this thing to take a task stack, this thing. Okay, so this thing can come up here. We don't need the physical address of this stack frame anymore. Yeah, so we're going to store the pointer to the stack frame. Here. And we need to do the same thing elsewhere over here. And this thing becomes null pointer. Okay. Yo, what's up? What's up, Paula? Thanks for popping in. I'm just confusing myself. Okay. So we are storing pointers to the task stack. And my code duplication is making this kind of messy. But now the final thing we can do is exit and task exit. Come here and task pool destroy current task p stack. Current task. Yeah, this could be all cleaned up. It's a little bit inconsistent. So when we do a task exit, we assert that we have a current task to exit from. This is interesting. This is no longer true. Actually, maybe it is true. The idle task always gets task 0. So I think that actually is true. But hold on one second. So we're destroying the stack. That's a little bit tricky, actually, because we're currently running on the... Actually, yeah, how does that even work? We're trying to destroy that stack. How do we destroy the stack while we are running on it at the very end? Because task exit is called by a task when it wants to exit. So we can think about this. Like right here, for example. So we're in a task and we're trying to exit. We call task exit. And so we're still all on the stack of that task. And then it's time to destroy it. Yeah, that's a little bit... sketchy. Yeah, what do we do? What could we do there? Some options. Maybe the cleanest option. Switch to some kind of clean stack for the scheduler. Yeah, that is interesting because a bunch of code still executes. When a task exits, we still have a bunch of code to execute to clean up the task and even run the scheduler. So that's a pretty substantial amount of code, actually. All right, 20 seconds, be right back. As usual, maybe a visual will help. So we got memory. Our task is executing here. This is the task. And it has a stack pointer, and it's doing whatever task stuff it's doing. And it's time to exit the task. It calls task exit, and we sort of drop into the scheduler. Yeah, I think, yeah. And so the idea is like it's a bit yeah. So to clean up the task itself, we need to delete ourselves from the linked list of tasks and enter the scheduler. And so deleting the task is doable. The task state is no longer really used. So it's pretty much fine to destroy that because the rest of the scheduler is not going to use it. We unset the task pointer. But the stack is a bit of a different story because the stack is actually used even by this running code. So I think the options are or have some deferred stack cleanup where something along the lines of we mark the stack as like it's sort of done, but then on some later point, another task potentially, or the scheduler, is going to clean up that stack that was marked as ready to be destroyed. Yeah, that's interesting. Okay. This seems cleaner. Switching, somehow having the scheduler as like own task with a well-defined stack and everything seems a little bit cleaner, but it's a little bit more complicated to have the dedicated scheduler task. It's pretty convenient to just be running the scheduler on top of the existing task that a stack has, which we do during yield, for example. And it's just kind of convenient to do that. And so I wonder what the deferred stack cleanup would look like. Let me check the chat. Going deep into low-level C++ while my friends are doing React Node replacements. What's up, Mathru? Yo, Mark, just came to say hi. Keep going, man. Thank you, Already Mystic. What's up, Scientist? Is systems programming even viable from a tier 3 college, or am I cooked? I think whether you're cooked or not depends on your mindset, and that applies to anything. So if you think you're cooked, you're going to be cooked. So there's so many people that do systems programming that don't have formal backgrounds from the top level universities. So just keep that in mind. Okay, this is turning out to be quite a lot of things all at once here, and so I'm getting a little bit overwhelmed. So we have the stack correctness topic, deferred or clean scheduler stack. I think, I mean, we can even just run the kernel and see what happens. I think this could technically still keep working, even though we technically destroy the stack. In practice right now, nothing else is concurrently going to try to use that memory right here. So just for the purposes of sketching out the idea, the idle task was running. Let's go back and reactivate the original test we were doing, which had a bunch of these tasks that were all just sort of yielding and doing their loops. And I would just be curious. Oh, cool, wow. We got an ETL assert that fired. That's the first one. That's wow, that's actually kind of cool. I have never actually seen that happen before. I invested into like a bit into setting up a little bit of integration with ETL so that that's interesting. I wonder if I can get a stack trace. Yeah, okay. So the baby, but the Byaga, are you putting a kernel? Not quite. I'm trying to do a lot of it myself. I'm using AI for assistance sometimes, but I'm trying to not vibe code it. So yeah, our create task was calling create on the task stack pool, and we're getting is the kernel entirely of C++? Yeah, pretty much. Okay, let's see what happened here. So each thread does a little bit of a yield on the first loop. And then we do a couple rounds. I think I want to print out some sizes in various places. So there's a couple members like empty, full. Okay. Size and max size. The pool has room for 4 things. So we can see that in this round, task 1 is coming around to its final iteration. Let me see. How much years of experience do you have with C++? Probably like 7 or so, I would say. Okay. So I just need to think through this a bit more clearly. So, okay, so, test 0 calls create task. And this one is failing. Oh, I see. The reason it's failing is because I made a mistake, and in my this is this weird init task thing that I just made. This was the purpose of this was to it's to be used to initialize the idle task. The idle task does not use the task stack pool. The idle task has its own stack, and so it wasn't correct to do this. It's this. So the task sorry, it's this line that needs to be different. P task equals to M idle task stack. So what was happening? Okay, so there are 4 slots for tasks. I filled 3 of those up to run the task. On the final exit of the first task, so the first task had finished the loop. It's creating a new task to replace it, and then it's exiting. So there's one more slot left for a task because there's 4 tasks. But the problem was that it sort of actually looked like this. So each of these tasks was over here, and the idle task, which is a separate thing now, was actually using the first one. And so when it came time to create a new task, it tried to go and allocate from the task pool, and they were all filled. The way it really works is that the idle task is just separately stored, and it has its own separate stack. So it should not be using the stacks from the main pool. And there it works. Oh, okay. So So it seems like this is kind of working. It's exactly the same as what we were seeing last time, but the stack management is a little bit better. We're no longer allocating a stack inside of the task, which is a bad idea. We have a separate allocation area for task stacks. And so it's kind of hard to see, but we're now using it here. So we have our list of tasks. We have our separate idle task. We have our pool of task stacks. And then when it's time to create a new task, let's see, instead of doing, okay, okay, it might not be visible. Instead of getting the task.stack, we get it from the pool. Man, this code is awful looking. It's so messy. I've just been trying to get this to work. Yeah, I'll need to do a bunch of cleaning up. Probably will do that off stream. But I guess just to recap, VA80 back when I break spend feeling, good for you. Important to do that. Yeah. So now we have, yeah, so now we sort of have a semi-functional thing working where tasks, I guess, what's the new diagram look like? So what is the diagram? Maybe I can really clean up this diagram. So here's how it kind of looks now. I guess I'll just delete a lot of this. Everything is still currently living in the kernel, like statically allocated, which is sort of not good. But we have a large block now for the scheduler. I'll kill the palm tree because we're getting close to the end of time. Also, I need more room. Okay, but and now we have here's how it looks. We have 4 stacks. Pretend these are a page size each. We also, and these are much smaller. Yeah, I'm making them a different color. We have our actual tasks, and we also have 4 of them right now. So fixed size allocation for our tasks. That's sort of how it looks right now. And stack 0, etc. And then when it's time for a task to run, RSP is going to point into over here for the various tasks. And This is an improvement over the initial prototype, which was more dangerously running things directly out of the fizz map. The current implementation is not so much safer because the stacks are all contiguous against each other. But at the very least, if you overwrite a stack and you go past the end of the stack, you don't corrupt arbitrary memory, you corrupt the top of another stack, and we can fix this by adding a guard page later. It's actually not even so hard. We could even just do it now. And so this is not a fully functional guard page, but what we could do is now we sort of balloon things a little bit. We have a guard page right after the stack. I think this should still completely work. There's nothing so wild about it. It's not super functional yet. To really make this functional as a guard page, we need to actually unmap it from the address space. Currently, my v-address space does not... actually, do we? Okay, never mind. I actually do... I forgot about that. I thought I didn't because I don't really handle like the reference counting well. If multiple address spaces are referencing the same physical page, that requires some reference counting. I don't handle that, but we don't have multiple address spaces just yet. So that's actually kind of interesting. We could even try to test that out right now. Well, chat is getting popular. That's crazy. This sort of happened last week a little bit too. It was like almost the end of the stream. And the chat started to get some traction. I wonder if there's something in the algorithm around that. Naturally, it's because of the A80. Okay. Let's do a bit of a test. So let me just to illustrate this. So the idea is to have a bit more safety with these stacks. And so the idea is like after every, okay, that's hard to see. After every actual stack, there's a guard page. Okay, that was too much. So this is sort of how things would look. And this is sort of the end goal. We have stack, we have spacing between the stacks that get unmapped from memory. I think I just need to make this huge. This is a huge problem. I don't have a solution for just yet. Cleanly handling the task exit. So I think the final couple of things we might do on stream, we could take a look at, okay, we could try to do this garbage thing super quick. I think it might not be that hard. What we need to do is going back to the scheduler. So our scheduler now has support for a v-address space. Scheduler has a v-address space it can use to manipulate the mappings in an address space. What's up, Job and Jacob? You're using AI? Yes, a little bit, just enough. And now that we have access to a v-address space, we could use that basically kind of right here. What we would need to do is v address space dot unmap p task stack top. No. Nope. Okay, so technically, wait a sec. Actually, yeah, wait a sec, yeah. So the way I've done it right now, there's the stack and then there's the guard page right after the stack. In memory, the stack is going to be at a lower address, then the guard page is going to be at the right next higher address. And so it actually is correct. P task stack top is the pointer to the first address of the guard page. Okay, I'll do a sloppy cast because unmap takes a vert adder, which is constructed from a UN64T. So let's do an experiment. Anyway, so this is happening in create tasks. We're creating the task, we're setting, and we're calling unmap, but we're doing this every single time. Technically, it only needs to happen the first time, but I think it's not a problem if you try to unmap an address that doesn't exist. It'll just return false. So let's try something right now. Let's just try something real quick. So the very first thing I just want to try is what happens if we dereference, like, dereference a random unmapped page. Can I have it do that? What would be a random unmapped page? I just wanted to see what kind of fault would appear. And I guess probably an unmapped random page would be, oh shit. Okay, it's way too fast to see. Let me just, so what's a rant? Like, we could try to dereference right below the HHDM base. That should be, let's, Yeah. Oops. Oh, sorry, brother, did I miss your question? What will be the advantage of yours over Windows 11? It'll probably be easier to learn from, I think. I'm not really trying to compete with Windows 11. So, so first things first, I just want to see, this is going to crash, to be clear. My prediction is we're going to see a double fault because I don't have a page fault handler yet, I think. So it's going to trigger a page fault, and then that's not going to be handled, which will trigger a double fault, I think. So just to kind of just clarify what happens if there's a bad memory access, I think this is what happens. Okay, there's a GP fault. Not quite what I expected, but doesn't really matter. Okay, cool. So now what I can try to do is I want to take a task. I want to intentionally wait. I think I did the guard page wrong. The guard page needs to come below the stack. Yeah, that, to be very clear about how that works. Sorry, I think that was kind of a stupid mistake. So, stack pointer starts at the top of the stack and works its way down. And we want to break if things get here. So we need to make sure the guard page is below the stack in memory. My previous struct layout had the guard page above the stack in memory, so that was not correct. Okay, so what I want to do first off is get current RSP. Okay, that's one way to do it. 86 RSP. Okay. Read RSP. So I want to read RSP and auto p equals RSP minus k page size. We're gonna basically just go down one page into the guard page, and we're gonna do the same thing. And I'll maybe log a few things. Log RSP. Okay. Log P. Okay, cool. So now what we're going to see the kernel task attempt to dereference memory that's inside the guard page. This should actually succeed because I have not unmapped the guard page from memory yet. So what we should actually see is the panic 1, 2, 3. We see the panic 1, 2, 3. So that's good. And you can see that this P is one page lower. There's an 8, there's a 7 here. So we're one page lower. Now what I want to do is I want to test my change where we unmap the guard page, and I think I need to actually just redo this now. So p guard page adder equals, oh wait, yeah, that's actually really easy because it's just in the task. Okay, that's actually super easy. So now we just get the pointer to the guard page and p guard page. Now we unmap it from the address space. Let's print out some information here. Let's just print out log the guard page. Okay, so we're gonna get some logging here from some guard pages. I'm gonna unmap the guard page. So now my prediction is that when we run the kernel, this is going to crash, and we're going to see the GP fault instead of the panic 1, 2, 3. So we're going to see some lines of text saying guard page blah 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 blah. We're going to see RSP. Maybe we'll print out the stack too. Log the stack bottom adder. Does it know how to do that? Good. Okay. Stack bottom is just stack.data. Cool. So we're going to be logging the stack bottom and then the guard page bottom, which should be one page below that. Like, I think 3 times. Then we'll see an RSP that is going to be within the first one of those. And then the P, which is within the guard page for the first task. So let's just see that. So that didn't work. We got to the panic. Let's just check this out. Right, so this is the particular one. 19,000, 18,000, okay? Okay, and it seems like we are accessing P, which is in the 18,000 range. And that succeeded, which I think it means I didn't engage the page tables. That's probably why. Let's just assert that this succeeds, actually. Just to be sure about that. Yeah, I think what I need to do, I need to remember to engage the page tables by reloading CR3. Let me do that. I don't, how do I even do that? Maybe I can, okay. So, oops. So my page table code, I have a pointer to the MPML4 table. So it's not so difficult. All I want to do is just reload CR3, and just the question is, where is the easiest point to do that? Where actually, so we just directly read CR3. Okay, I think, okay, this is going to be kind of a hacky way to do it, but I think I might just do it in line here, right here. So I will do it right before this line. And do we have a load CR3 function? We do, but not for 64-bit. So I'm going to ask, I need some help. Generate the 64-bit version of this. Or wait a sec, what? This, why did it use it even 64 already? Anyway, so now we have the 64-bit version of load CR3. And we can just do load CR3 64, read CR3 64. And that should reload the new page tables, in which there's no mapping for the guard page. So let's just see that. That would be pretty cool if that, look at that. And it double faulted, which is interesting. So that totally worked. To be clear, that totally worked just now. That's exactly what we want to happen. I think it's a double fault because I didn't handle the page. So maybe just super, I don't know if it's easy to add a page fault handler interrupt. I think I need to interrupt hub for some reason. I'm just going to quickly ask the AI, please generate a basic panicking page fault handler. Let's see if we can just do that. To do that, we would just need to find the interrupt number for the page fault. We would need to add a little bit, like a small stub for it in the assembly. And we would need to add a little handler function. And I think that should be clear enough for the AI to figure out. So, so it should just be able to do that super quickly. And so when it does that, we should actually see page fault here instead of double fault. I think it's pretty close to being done now, actually. It understands the structure for how I'm doing things. Whoa, okay, we got, that is not acceptable. I don't know who posted that. We're going to, yeah. Yeah, I think it's pretty much done it. It has added a new handler stub, and we have a new function called handle page fault, which is going to print page fault. So let's just see if that worked. Look at that, page fault. So that's the specific fault that gets triggered in these kinds of scenarios. I actually don't know why it was previously GP faulting when I was accessing that address. That was right sort of below here. But this is really good. And so this is just sketching out what happens when you have a working guard page. When you have a working guard page, it will catch it if you accidentally overflow your stack and go too far down and start accessing memory, like invalid memory, or just off if you just go off the end of your stack, which is something you want to know about if that happens. So that's pretty cool. Check that out. We can even see, I don't know if we can see, CR2 gives us, I don't really know what that number is. it looks, it's like P, but without all the high numbers somehow, or the high bits. So I don't know if that's read CR. Oh, CR, because read CR2 is the 32-bit version. So yeah, make the 64-bit version, please. That's why. Yeah, this x86.h file that I'm using is for 32-bit, and so it, yeah, a lot of its stuff is going to be. Oh, okay, now it updated this thing. So now when we run it, we're going to see the full address of the faulting address, which is this P address. So that's kind of cool. So we just sort of prototyped some basic guard page handling for the tasks, which is kind of cool. So, all right, y'all, I think that's going to be it for today. I'll just check the chat really quickly. Which AI chat? I'm using GitHub Copilot. That's going to be it for today. I want to thank you a lot for tuning into the stream. If you enjoy this content, please subscribe to my YouTube channel. I would really appreciate that. And you can always feel free to join the Discord if you want to do that. Thank you, Water Bottle. Appreciate that. Thank you, VA80, for all the encouragement. I hope you have a great day and a great week, and I will catch you in the next stream. Peace.